which is going to continue with, I mean, slightly different from the schedule. It's going to continue with the geometric computations of the pair of stamps. And afterwards, we're going to insert an unscheduled continuation talk by Navi that kind of ends. Then we'll continue with the schedule slightly later.
Okay, thank you. So I want to recall where we're up to. So we had this, we'd worked out that category we're really interested in computing can be obtained from this Fukaya category of projective space with some orbifolding around these hyperplanes. And so we started trying to understand this guy, which is simpler. So we constructed some immersed Lagrangian sphere inside the complement of the divisor over here. And what we were in the process of proving was certain things about the Floer cohomology of this Lagrangian. So the first thing was that as an associative algebra, it's an exterior algebra on n generators. The second thing was a certain higher A infinity product where we take in n inputs and it tells us a certain thing about what the output can look like. And the third thing was that when we take the differential of one of these generators, theta I, we get qi, this is one of our parameters corresponding to how curves go through the divisor, times the identity class.
Oh, plus something.
Plus higher order in Q. And note, this is not exactly in the category we're trying to compute, but we will relate them later on. And so I want to make the connection with Nati's talk and what he'll say in future as well. So we have some A infinity structure on this guy, which is some big complicated thing with infinitely many operations in it. But if we only want to determine it up to A infinity quasi-isomorphism, we actually only need a finite amount of information about certain of those structure maps. In fact, knowing these mu2s that say you get this exterior algebra this mu n and certain consequence of this computation in here is enough to determine it up to A infinity quasi-isomorphism. And the way you prove that is by studying deformations of A infinity structures in Hochschild cohomology, which is what Nati will talk about. Okay, but what I want to explain in this talk is how you actually, which holomorphic curves you're counting to prove these 3 bits of structure. So we constructed this Lagrangian immersed sphere by taking the double cover of the real locus inside Cpn-2 and pushing it off by a Morse function so that it avoided the divisors in here. So let me keep a drawing of the Morse function over here so that we can refer to it. Maybe want an even bigger one than that. Okay. So this was a picture of stereographic projection of the 2-sphere. These are the real components of our divisors as they intersect the 2-sphere in great circles. And our Morse function has critical points in each of these regions. And we can label the regions by the variables are positive in that region. So the hyperplanes correspond to where the variables are 0. So inside here, D4 is going to be positive. Outside, it's going to be negative. So here we're going to write this one, D4 only is positive. Here, both 3 and 4 are going to be positive. Here, 1 and 4, here 1, 3, 4. Here we go outside 4, so we get 1, 3. Here we go outside 2, so we get 2, 4. Here we go outside 4, so we just get 2, and so on. You can fill in the whole picture. And then this Morse function has flow lines that look... So this sphere sum is 0, sum squared is 1. Yeah.
For all but D4, they're positive outside the circle?
Yes. So So here are some Morse flow lines of our function. So it's always flowing transversely across the hypersurfaces, which means when you push it off, it avoids that divisor. And you can see what the Morse flow lines look like, etc., etc. Sorry, I just want to have this picture available so I can draw things on it later. Okay. And there's this point at infinity out here.
Could you please give a short reminder about what was the Morse function? I remember it was sum of some functions.
Yeah, it was the sum. It looked like this. So the function looks almost constant in the interior of this region, and then when we cross the divisor, suddenly it bumps up. So these flow lines are going very, very slowly, and then whoosh across, and then to the critical point. And I explained what kind of objects we need to count. We need to count J holomorphic disks with boundary on RPn-2, which of course are things we can enumerate, together with flow lines, well, together with a lift of the boundary, which means this kind of thing. We need a lift of the boundary to Sn-2. And so the flow cohomology was
critical points appear twice.
No, you have so here are two antipodal points.
Okay.
They're both critical points,
Yes.
and this is one self-intersection point that appears twice. So the critical points of F were in one-to-one correspondence with subsets that are not empty or everything. And then we had an extra Morse function that tells you how to push L off itself, and that gives you the Morse cohomology of the sphere. Which has two generators which we identify with generators corresponding to the empty set and to the whole set here. And now so we have this, so we're counting these configurations of Morse flow lines and holomorphic disks, and we have a lift to the boundary, and then whether we have a Morse flow line of F or H depends on whether the two sheets of the lift of the boundary on either side of that flow line are to the opposite sheets or to the same sheet. If they're going to opposite sheets, it has to be a flow line of F. If they're to the same sheet, it has to be a flow line of H.
Can you explain why?
So if you draw so here's your real locus. Here's your Lagrangian, which is the graph of df. And then here is your push-off of the Lagrangian. This is a push-off by dh. So if you have a very thin strip region where the two lifts are to the same sheet of the Lagrangian, then that means you're looking at a strip that kind of looks like this, and the vertical direction is in the direction of dh, so the fact it's J holomorphic means the horizontal direction has to be in the direction of grad h. Whereas if you have different sheets, that means you're looking at a very thin holomorphic strip like this, and the difference between them is df. So again, the horizontal direction is grad f. Okay.
Please show in the picture those lifts of the boundary.
Sure. So there are two. So here's the double cover. Here are the two sheets. And you have two sides of the boundary of this thin strip region. And, you know, maybe if they're both the same sheet, then this would be A and this would be B. But if they're different sheets, then this would be A and this would be B down here. Okay? So you also need to count, well, if we're counting things that we want to contribute to the Fukaya category of the complement of D, we need to count these things that have intersection number 0 with the divisors. And there was this thing there were sort of three possibilities for picking up an intersection number. You could have a piece of the boundary of your curve, one of your disks, crossing the real part of the divisor in positive direction. You could have a flow line of F crossing the divisor in any direction, or you could just have an interior marked point, interior intersection point of one of these disks with the divisor. Yep.
Explain the leftmost case.
This one?
Yeah.
This is where this disk hits the divisor somewhere in its interior. That contributes to the intersection number.
So I thought it's the second case. So now explain the second case.
The second case is where the boundary of your disk hits the real part of one of these divisors. And then if the boundary is crossing in negative direction, it's not going to pick up an intersection point because it's getting pushed above the divisor. But if it's crossing in positive direction, it's getting pushed below, and this does contribute to the intersection number. So last time I explained a grading computation that meant the only contributions to the product could be of this form that looks extremely similar to the exterior algebra. But we need to check that this coefficient really is plus or minus 1. So we need to count things that look like this. And now I should see my notes. So basically these turn out to be lines. So I'm going to introduce some subsets of the sphere, a notation for certain subsets of the sphere, linear subsets.
And minus 2?
Yes. Thank you. So we have the subsets are indexed by a bunch of subsets K1 through KK, and it's the subset so that for each of these subsets, all of the corresponding coordinates are equal. So complement of K. So the ascending manifold is some open subset of this guy. The descending is some open subset of this guy. And you can work out just purely topologically what the degree of this curve has to be, and it turns out to be degree 1, so it's half of a real line.
Say it once more. What do I have to compute now?
I have to count how many
Yes.
configurations like this there are.
Yeah. So how do we do it? This is how we use this is Pj, Pk. So what are the geometry? I have to do some. So okay, we deform it to this space. Okay.
So just topologically, you can work out what the degree of this map would have to be. And it's a degree 1, so it's a half of a real line. So we are looking for a real line that intersects the ascending manifolds of these two guys and the descending manifold of this guy. And these ascending and descending manifolds for this Morse function we've cooked up are linear spaces. So we're looking for a line that hits these 3 linear spaces. So this is just linear algebra. and the line turns out to be the line where all coordinates in J are equal, all coordinates in K are equal, and all coordinates in J union K, complement, are equal. So we're sort of partitioning the coordinates into 3 sets, and within each set they're all equal. So this gives a line. So let's draw an example. So if we were trying to compute the product of P2 with P4, and we want the output to be P24, which actually means the output kind of gets dualized, so it sort of means hitting this guy. And so here is our line that goes through these guys. That's this F2, 4, 1, 3. But now we're not done. We also need this lift of the boundary. That has to cross all of the divisors negatively. So what could the lift of the boundary be? So we have, so starting with P2 and going to P24, we would have to go in this direction. Sorry, I should use a different color for this. So we have to cross negatively, so we go in this direction. And then at this point, we have this self-intersection. So that means we have to switch to the other sheet, which is opposite to this guy. So that's at infinity. And then we have to go, so we've gone down this side, we've switched sheet, and now we need to go from P13 to P2, which we do, I'm a bit confused. So we go from P13 to P2, which is opposite to P134. And then we have to go from P2 to P13, which goes down here and comes back up the other end. Why are we not running into this extra? So the extra one way out here is P1, 2, 3. I guess there's no problem with that. Yeah, okay. So now we run out to infinity. We hit P1, 2, 3, which switches back to here. So now I've gone all the way around that boundary of that triangle. And you can check, we always cross these divisors in negative direction. So we didn't pick up any intersection number. Okay, so using this, we've checked the product of Pj with Pk, it's Pj union K. Now we need to check some sign to make sure this is really an exterior algebra. But let me not say that that would require going into too much detail about signs, so let me not say that.
algebra essentially fixes sides automatically.
No, I mean you could have something like this algebra is different from exterior algebra, of course. So, yes.
I understand where the boundary goes, but where does the interior of the disk go?
So this is a degree 1 curve. These hyperplanes are hyperplanes. So the disk hits each hyperplane exactly once. And you can see it hits each hyperplane on the boundary, so it doesn't have any interior marked points. Or maybe your question was, I mean, we have this line that gives us a complex line, a complex CP1 inside our projective space. And we need to choose 1/2 of that CP1 so that the boundary is oriented in this direction that goes across the divisors positively.
Nick,
Yep.
the definition of the set FK1 to KK, so it's the set
Diagonals.
where X, I is like J for all I and J belonging to...
One is
KL to one of these sets
Okay.
for all. So for each of these sets, all of the corresponding coordinates inside it are equal. So for example, this one is a line because it's so maybe it would look like that. So this would be F1, 2, 3, 4. Oh, just lost my colored chalk. Okay, so that was about the product. The next thing is this mu n. Well, if you're going to count, so first, if you're going to input some combination of the generators theta I, they have to all be different, otherwise you can't have it for grading reasons. And the output has to be the identity.
If you try to draw the trees that contribute and label the boundaries, you just run into combinatorial.
So even before you start talking about trees, there is this grading in the Lagrangian-Grassmannian of the pair of pants. And if you just compute the gradings of all these generators, so I wrote them down last time, the only ones that can add up in the right way are these ones. So So, a priori, one may have to count things like this. in this,
The disk is 2?
it's n.
Oh, it's n.
It's 2 in the case, in the two-dimensional case. So n minus 2, I guess. So a priori, one could have configurations like this, but you can work with the topology of these disks, and you can work out that you can only have one bubble. So it has to look like this. This guy has degree n minus 2. And these guys are all Morse critical points of index 0, so actually there are no flow lines, there are just point constraints. And now we have n plus 1 point constraints for a degree n minus 2 real curve. And there's this thing called Veronese's theorem. Which says that there's a unique such curve. Now, so for example, in this two-dimensional case, so n is 4, there's a unique degree 2 curve through 5 points in CP2. There's a unique conic through 5 points in the plane. But of course, we're not done. We need this lift of the boundary that switches sheets at these n points, but not at this one. And this kind of miracle happens that, I mean, so you can write down what this degree n minus 2 curve is. You can write down a formula for it. And the formula sort of treats one of the marked points as being distinguished and gives a natural lift of the boundary that switches sheets at all the other marked points and also crosses all the divisors in positive direction. It's just works. And now that curve, whatever it was, it intersected these n marked points. It intersected them in some order on the boundary. So whatever that order was, you get a mu n for the theta I in that order and no other order. So when you kind of symmetrize everything like this, the output is what I claimed it was, product of Z1 through Zn.
So your curve is a kind of real part. So you have a real CP1, Yeah.
and then you take half of it.
Yeah.
One half of it will cross the divisors in the correct direction. So finally, we had this relation. So again, the grading helps us. Basically, it says the only first order term that could possibly contribute to mu1 of theta I is some multiple of this qi. We just need to work out what the multiple is by counting these configurations. So once again, these guys are have constant Morse flow lines. You can also check topologically the degree has to be equal to 1. So now we have 2 points and a line through them. So of course there's a unique such line. So for example, in this picture here, maybe we want to compute mu1 of P4. So we have P4 and we have this random point P phi. That is the minimum of our Morse function. We have the unique line through these 2 points. And now we need to construct this lift of the boundary of this disk that changes sheets at this point. And there is exactly one lift, which is this one. That contributes. So this one goes from P4 to its antipode, which is the point at infinity in this picture. And it crosses all of these divisors positively with the exception of D4. So it goes out along this one, so out of this guy, but in along D4. This observation that D4 is the only one that has, that's kind of pointing in. So in particular, well, you get the unique real line through Pi and P phi, and it crosses Di once negatively and all the others positively. So this is why it comes with a coefficient of Qi, because it just has intersection number 1 with that divisor. So this is the one I drew this picture of the pair of pants in dimension 1. And this Lagrangian kind of goes sort of in and out between the divisors like this. And so I'm taking this point here, say, P3, and then I'm counting this, so this disk is the one that has boundary, I think I've run out of colored chalk, but so it has a crossing here, changes sheets, and then it goes around like this. It's like the upper half of the sphere, and it goes around like this, and it dips below, and then dips above these guys. So it goes above these 2 guys, but below this one, so it picks up an intersection number with the corresponding divisor. Okay, so that's the completion of the proof of these computations of parts of the A infinity structure for this Lagrangian. So maybe the next step involves deformation theory, so maybe this would be a good time to take questions and then go back to Nati's talk. Does that make sense?
Do we have any questions for him?
why only the negative crossing counts?
That was this picture. If you're counting a disk like this, then it hits the divisor. If you're counting a disk like this, it doesn't.
Can you say how to see that from the picture?
Sure. So the Morse flow lines point in the direction going out, going across the divisor positively. So D1, D2, and D3 all point outwards. D4 points inwards. Now, if you look at this boundary lift, so it goes from D4 to its antipode, and it switches signs, switches sheets at this point. So it goes across this guy positively. It goes, well, okay, it starts off inside D1, D2, and D3, and it goes out of them. It starts off inside D4 and goes out of it, which is crossing in the negative direction, because it's the only one that is oriented that way.
Okay, and so the lift, so you do the lift on one of the components from PI to the empty set?
Yep.
And then on the other component, it kind of, what happens then? Or, like you have a disk and there's like two boundary components between PI?
You're right. Sorry. Okay. What I should have said is that, okay, sorry, I should have drawn P5 over here. I should have said that you take the half of this line that goes through this point P5, and then you orient it, you choose which half of the disk by orienting it so that it crosses all of the PI positively except one. And that chooses which half of this real holomorphic sphere you take.
Okay, and then
the other half.
That line going out is just the other side, and P4, and like the other, like P4 antipode is at infinity.
Yes,
So when you've got there, you've already come back to where you started.
that's correct. Yeah.
Okay.
Yeah, so I mean, this line gets identified with this line in RP in -2. So we're just choosing one lift, so we just choose this. We need to just choose the half, yeah.
And there you go out through. You cross one more divisor there, and it's also in the right direction.
Yes. So
It's still going out.
D1, D2, and D3 are all going out. D4 is going in. So it's going out of D1, D2, D3, but sort of into D4.